Hello, AP Chem students, and welcome to topic 6.3, heat transfer and thermal equilibrium. So the learning objective for today is 6.3.a, explain the relationship between the transfer of thermal energy and molecular collisions. So here we go. So representing heat transfer, oh my word. Okay, there we go. So energy transfers can also be represented in particle view diagrams by using arrows to represent the relative speed of the particles in a species. So in the last video, we talked about representing energy transfers with graphs. And so this is with particle diagrams. So the length of the arrows changes in approximate proportion to the temperature, at least in AP style questions, okay? At some point in time, thermal equilibrium is reached when the thermal energy of each component is the same on average, meaning that their temperatures are also the same. Will every arrow be exactly the same length? No, because every particle is not moving at exactly the same speed. Remember back to the Maxwell-Boltzmann distribution graphs, but they should overall average to be the same when you've reached thermal equilibrium. So here's what a drawing like this might look like. So you start out with a sample at high temperature and a different sample at low temperature, and then the heat is transferred by the collisions. So you can see that happening here. So this red particle is colliding with the white particle, and that makes an orange particle. So heat transfer happens over time, and then you can see when all the particles are orange, the net heat transfer has ceased. So these two samples are now at the same temperature and have reached thermal equilibrium, and so we no longer have a flow of heat. Collisions are still occurring, but you don't have that heat transfer. So arrows at the high initial temperature are longer on average. They have a greater kinetic energy. Arrows at initial lower temperature are shorter on average, and they have less kinetic energy. So if you're asked to draw this on the exam, and we have seen a question like that recently, be sure that if you're drawing at a higher temperature, your arrows are longer, and if you're drawing at a lower temperature, your arrows are shorter. At thermal equilibrium, all arrows are the same. They have the high temperature side now has shorter arrows, and the lower temperature side now has longer arrows, and the average kinetic energy of the entire sample is the same, and so is their temperature. So heat transfer, again, occurs as a result of collisions between the particles. The higher energy particles transfer heat to the lower energy particles. You can see that happening here. So this is a longer arrow coming in. It's at a higher energy before collision. This is at a lower energy coming into the collision. It's got a shorter arrow. And then after they leave, this is not yet at thermal equilibrium. You can see that this arrow is shorter than that arrow, but heat transfer has occurred. And then over time, you will reach thermal equilibrium when the speeds of the particles has averaged to be the same. So this is called heat transfer or heat exchange, or transfer of energy as heat. Those are all the same thing. But again, remember that it happens because of collisions between particles. So that's it. Pretty short topic here. What should you be able to do with this? First of all, interpret particle diagrams using arrows that show heat transfer. Justify a transfer of energy as a result of the collisions between warmer and cooler particles. And then assign the direction of heat flow based on temperature data for two components of a system. And also, when it says interpret particle diagrams, you should also be able to produce your own particle diagrams that use the arrows to show that heat transfer. That's it. And I will see you soon for our next topic in thermochemistry.